Good afternoon, Southminster scholars, lovers of learning and seekers of truth. We are on the home stretch of this series, and for the next four, we're in the month of December, so we're going to be talking about different aspects of the universe. Today, it's the outer realms, the Kepler belt and the Oort cloud. The discovery of the Kuiper belt has taken place only in the last few decades. These objects, including Pluto, consist of small, icy particles. It's a world beyond the universe. Small, icy worlds beyond Neptune, even. Gravitational scattering sends these objects toward the inner solar system, where they become short-paced or short-pulse comets. The source of these comets, known as the Oort cloud, cannot be directly observed, but rather it is deduced from the statistics of the comet orbits. The Oort cloud extends nearly 1/5 of the way to our nearest star. Let's watch Dr. Summers as he explains and describes this phenomenon.
This is an amazing time to be studying the solar system. The space age has given us incredible access to seeing the worlds of our planetary system, seeing them up close and personal. Our knowledge, as you've seen in the past lectures, has exploded. There is so much new stuff, it really is hard to keep up with all the new discoveries from all the satellite missions. And yet, something even more monumental has been revealed by ground-based observing. We have begun to explore a whole new realm of the solar system. The familiar structure that we once learned has now been extended. And this is a turning point in history, when our views change at a fundamental level. It's similar to the discovery of Uranus, when we learned that other planets could exist. We now know that there's more. There is something new under the sun. I'm talking about the Kuiper belt. And it's not a totally new concept. The ideas have been kicked around for decades. Just after Pluto was discovered in 1930, an astronomer named Leonard discussed the possibility that Pluto was just the first of many objects beyond Neptune. In 1943, Edgeworth discussed the idea that large numbers of small bodies might have actually formed in the outer solar system. In 1951, Kuiper noted that a massive Pluto would scatter bodies outward. And I note that in 1951, Pluto was thought to be as massive as Earth, so it would have those scattering properties. Now, several other postulations and formulations followed, but it wasn't until 1980 when Fernandez got the idea correct. He predicted a belt of comet nuclei beyond Neptune that would serve as the reservoir for the short period comets that we observe. Now, many people don't like it being called the Kuiper belt, basically because he got it wrong. Some people call it the Edgeworth Kuiper belt, and nobody I know seems to call it the Fernandez belt, the guy who got it right. To be politically correct, some folks call the discoveries trans-Neptunian objects or scattered disk objects. My preferences, I would just rather call it the comet belt. That makes sense. It's sort of like the asteroid belt. Asteroid belt, comet belt. And really, that's what Fernandez called it in his paper. Incidentally, I'd also like to call the Oort cloud the comet cloud, but I'm not going to tilt at windmills. In this lecture, I'll call it the Kuiper belt and the Oort cloud, but you should be aware that there are some naming biases. The first object discovered in the Kuiper belt was, of course, Pluto in 1930. The second was Charon in 1978, but of course we didn't know there was a Kuiper belt at the time. The third discovery in the Kuiper Belt, and the one that signaled the existence of the Kuiper Belt, was 1992 QB1. Here are the discovery images of 1992 QB1. It was discovered by Dave Jewett and Jane Liu. They took these 4 images in a telescope on Mauna Kea over the span of 3.5 hours. Now you'll notice that the star over here on the left doesn't move in each image, whereas the dot pointed to by the arrow here, this does move in each image. The technique we're using here is essentially the digital version of the blink comparator that was used by Clyde Tombaugh to discover Pluto. Objects in the solar system will move across the sky on orders of hours, where of course stars will not move on that time scale. QB1 was found to have an orbit of 42 astronomical units. For reference, Neptune's orbit is basically a circle at 30 astronomical units. Pluto's orbit is elliptical, and it goes in as close as about 30 astronomical units and out to about 50 astronomical units. So you can see QB1 was smack dab right where Pluto was in the solar system. Jewett and Liu's discovery showed that Fernandez's predictions were right. And 6 months later, they discovered a second object in the Kuiper Belt. Now, once astronomers know that objects like this exist, well, others are going to join into the search. The main requirement for seeing these Kuiper Belt objects was a big telescope so that you could see these very faint objects, and lots of observations. You had to take observations hour after hour and night after night. Furthermore, you needed a lot of patience to be able to search through all these observations to be able to identify these objects. Here is an example discovery sequence for an object called Orcus. And as I move through this, if I blink forward and then backward through it, and then forward through it, and backward through it, the moving object becomes rather obvious to your eye. We are very attuned to seeing the changes in these images. But these images are digital images. They're taken by CCD cameras and processed on computers. So the procedure of identifying the moving objects is relatively easily automated. What we do is we write a computer program that first aligns all the images, and then we'll subtract one image from the other. And it will look for residuals between the images that are moving. Using techniques like this, within years, hundreds of Kuiper Belt objects were discovered. And almost all the searches were done using ground-based telescopes, simply because you needed a lot of telescope time, and it's very hard to get that much time on a satellite mission. Now, the objects that they discovered, well, if I put my tongue in cheek, I might describe them as massive mutant giant comets. Here's an artist's depiction of one, and its name is Kuiper, and it's about 1,300 kilometers across. Its composition is mostly ice with some rock. It is similar in size to the medium-sized moons of the solar system. And so its surface, as depicted here, is imagined to be similar as well. Mostly icy, a bunch of craters on it, lots of cracks. Now, Kuiper is one of the larger Kuiper Belt objects. Most of the Kuiper Belt objects we've discovered are significantly smaller. The Kuiper Belt objects cover about the same sizes as the moons cover, from kilometer-sized objects up to thousands of kilometers, except the Kuiper Belt objects don't cover the same realm. They don't cover the size of the 7 largest moons of our solar system. Now, I need to discuss one individual Kuiper Belt object. This is the object now known as Eris. Originally, it was called 2003 UB313. That was its discovery name. And then it was nicknamed by its discoverer, Xena. You'll find all 3 of those names referenced in articles and books. Here are the discovery images for Eris from the Keck telescope. And as I go through them, you can see there are just 3 images of a poorly resolved blob. But that was enough for a remarkable discovery. Because taking follow-up images and doing orbit calculations, we found that Eris was at a distance of 97 astronomical units. Again, Neptune is at 30 astronomical units. Eris is over 3 times farther away. It also has a very highly elliptical orbit. Here is a drawing of Eris's orbit, 2003 UB313 at the time this plot was made. And here is Pluto's orbit, and here are the orbits of working outward in Neptune, Uranus, Saturn, and Jupiter. And you can see that Eris was discovered near its aphelion, near its farthest point from the Sun. It actually goes out just a little bit further to 97.5 AU, and it gets in as close to the Sun as 40 AU. It is the most distant solar system object known. And it shows that Kuiper belt objects can be scattered out to very, very large distances. Now, if it's at that large distance, that means it has to be very bright to be seen, and therefore very big. Upon its discovery, its diameter was estimated to be up to twice the diameter of Pluto. We couldn't measure it with the original discovery images, but we put Hubble to that task. And here we show you the Hubble image of Eris. It's not that impressive. It's just a few pixels. But it's enough to estimate with a good degree of accuracy the size of Eris. It turned out that it's only 10% larger than Pluto. But the important thing is it's bigger nonetheless. Later, we found that Eris had a moon, and here is the image from Keck of Eris and its moon, which is named Dysnomia. And this makes it look a lot like Pluto, because here is a Kuiper belt object, and here it has a moon. So it has the same characteristics as Pluto, but bigger. And the discoverer started calling it the 10th planet. It isn't the 10th planet. What was really happening was this was the beginning of the end of Pluto being the 9th planet. But I won't discuss that today. We'll discuss that in the next lecture. Now we want to look at the whole population of these outer solar system small bodies. There's over 1,200 of them discovered so far, and we categorize them into several groups on the basis of their orbits. Here is the overhead view of the outer solar system. Again, these blue orbits here working from in out are Jupiter, Saturn, Uranus, and Neptune. Almost everything else you see in this plot was discovered in the last couple decades. All these objects outside of Neptune's orbit, all these red and white objects out here, these are the Kuiper belt objects. We really have discovered a whole new region of the solar system. You'll note that there's a pretty strong fall off in these objects, whether you're looking inside of 30 AU, inside of Neptune's orbit, or outside of 50 AU. Now, it's not just our observational biases. We would have seen the objects if they did exist outside of 50 AU. So from 30 AU to 50 AU is taken as the boundaries of the Kuiper belt, but you can see from here that it's not really absolute. There are some that go in and some that goes out. Inside of the orbit of Neptune, there are some that are scattered throughout. And then there are some that are highly concentrated around Jupiter's orbit. In this plot, there are also some blue squares. These aren't Kuiper belt objects. They are comets, and they sort of confuse the plot a little bit. Also, you'll note at the bottom of this plot, there's this sort of gap in the Kuiper belt. This is not objects that are missing. This is due to the plane of our galaxy, and the dense star field in our galaxy makes spotting the Kuiper belt objects difficult there. So let's compare this outer solar system plot to the inner solar system plot. Wow! The first thing that you notice, there's a lot of asteroids, all these green objects. We know of over 150,000 asteroids. But once you get over that, you say, okay, well, it's still got that same sort of fuzzy appearance as the Kuiper belt. And there's stuff scattered inward and stuff scattered outward. So the two belts are roughly comparable. The outer circle in this diagram is the orbit of Jupiter. And at the orbit of Jupiter, you see these blue objects appear in two groups. One is ahead of Jupiter in its orbit, and one is behind Jupiter in its orbit. These are spots where Jupiter's gravity roughly balances out that of the Sun, and they're relatively stable positions for these Trojans to occupy. Now, we call them the Trojan asteroids, but observations and theory really indicate that they're likely made of ice. So perhaps we should call these the Trojan comets. Now, the outer solar system families can be examined in a series of 3 plots here, and they all have the same color coding to them. So let me take a little time to explain the color coding. The y-axis on this plot is a quantity called color index, and you don't really need to worry about it. But just so you know, the larger the color index indicates a bluer color for the object, and the smaller index indicates a redder color. The x-axis is the one we're concerned with on this plot, and it's the semi-major axis of the orbit. And this is how we discriminate the families. Over here on the left, plotted in cyan, are the Trojans, and these are the ones that share the orbit with Jupiter. The green objects are centaurs. They are distributed inside the orbit of Neptune. And Triton, Neptune's largest moon, that was probably a centaur that was captured into orbit by Neptune. These red objects here around 40 AU, you can see they have a very, very tight distribution. These share a 3-to-2 resonance with Neptune. For every 3 orbits Neptune makes around the Sun, these objects make 2 orbits around the Sun. And that locks them in to their orbit. These are called resonant Kuiper belt objects, and Pluto is the most prominent member of the resonant Kuiper belt object family. Just outside that, we have the magenta objects, and these are your classical Kuiper belt objects. These are the ones that would be the corollary to the main belt asteroids, the ones shown in green for the inner solar system plot. Finally, at the outermost, we have the scattered Kuiper belt objects. These extend out well beyond the classical cutoff radius of the Kuiper belt, and Eris is a scattered Kuiper belt object. If we then plot this same color index versus the orbit eccentricity, you can see other correlations. See, the semi-major axis is just the average distance from the Sun, but the eccentricity indicates how close and how far away you get from the Sun, the difference between your perihelion and aphelion. On the left-hand side here, you can see the magenta and the cyan, and you can see that the Trojans and the classical Kuiper belt objects, their orbits are mostly circular. They're relatively small eccentricities. Moving to the right, you can see the red objects, the resonant Kuiper belt objects, and their orbits are somewhat elliptical. But the centaurs and the scattered Kuiper belt objects are very elliptical. These have ellipticities ranging from about 0.3 on up to about 0.6. This can be understood in terms of the degree of interaction with the planet Neptune. These resonant objects, they have some interaction, so their eccentricity is pumped up a little bit. The centaurs have a strong interaction, and they're sent inward of Neptune's orbit and develop these highly elliptical orbits. The scattered objects also have a strong interaction with Neptune, and these are then scattered outward, well beyond the orbit of Neptune. So what we see is that Neptune plays a dominant role in determining the structure of the Kuiper belt. If we look at an overplot of some Kuiper belt object orbits, you can see how they key off of Neptune's orbit. Even these scattered objects that go way out for their aphelion have their perihelion in the vicinity of Neptune's orbit. Neptune's gravity dominates the motion of the objects in this region. We have one other comment about the orbits, and it's really a non-comment. Here we plot that same color index, but now we're plotting it against orbit inclinations. And you can see that the orbit inclinations go from 0, which would be in the plane of the ecliptic, up to about 30 degrees. But you can also see that the orbit inclinations here do not show any trends by family. All of the families cover essentially all of the region. So the whole outer solar system is not flat in the plane of the ecliptic, but it's rather puffed up plus or minus 30 degrees from the plane of the ecliptic. Now, the Kuiper belt is the source of the short period comets. objects are scattered inward by Neptune to become centaurs, and then they're scattered by the giant planets to go to the inner part of the solar system and become comets. The question then is, what about the long period comets? Where do they come from? To understand this, you have to look at some comet statistics. This histogram here shows the comets, and the x-axis is a quantity called the inverse semi-major axis. It's 1 over the semi-major axis, and we use this quantity because when you get these really long orbits that can be 5,000 or 10,000 or 20,000 or 30,000 years, your plot stretches out a long, long way. But if you take the inverse, all of the really long orbits bunch together. So you can see two peaks in this plot. One is at an orbital period about 7 years. This is a peak in the orbital period of short period comets. The other one is essentially at infinite orbital period. Most of the comets we have ever seen have these really, really long orbits. And if they've got these long orbits, it naturally means that they're very elongated orbits. Here is a plot of the orbit eccentricity for comets. And you can see that there are, a few that have reasonable eccentricities. But over here on the right-hand side, you can see towards one, which is essentially so elongated that you're almost like a line. This is where most of the comets pile up. We can only see comets that pass through the inner solar system. So if they have these very large orbit sizes, they also have to have large eccentricity, otherwise they wouldn't come into the inner solar system. Most of the comets we have seen are so elliptical that the orbits are almost hyperbolic. The other important piece of information is about the orbit inclinations. As shown in this histogram, you can see that there are a significant number of low inclination comets. Those, say less than about 15 or 20 degrees here. These would be dominated by the short period comets. These are the ones that would be orbiting in the ecliptic plane. The rest of the comets really show no preference for inclination. Their orbits are tilted at all directions. Now you'll note there's a small drop in the data near 180 degrees. Those orbits would actually be retrograde orbits in the ecliptic plane, and such orbits would suffer increased scattering by the giant planets, so it's understandable that there might be a few less comets in those type of orbits. So if we put those ideas together, most comets come from way out in the solar system. Most comets come from any direction on the sky. This naturally suggests a reservoir that is spherical for the long period comets. And we call it the Oort cloud. Now this time, the name is actually correct, because Jan Oort is the one who predicted it, and he did get it right. Here is an artist's impression of the Oort cloud, and the idea is simply that it's a huge cloud of comets. And how huge? Its radius is about 50,000 astronomical units. That totally redefines the idea of an outer solar system. Previously, we were talking about 30 to 50 AU. Now we're talking 50,000 AU. That extends 1,000 times farther than the Kuiper belt. Now I want you to note that in this diagram, the scale on this drawing is logarithmic. So you can see the planet orbits in here. That's within about 10 AU, or out to 30 AU for Neptune, and then out to about 100 AU for the Kuiper belt. And then you get 1, 2, 3 more factors of 10 to get out to the scale of the Oort cloud. We believe that the outer Oort cloud probably contains billions of comets, and that, as you can see from this drawing, that the inner parts of the Oort cloud are concentrated along the plane of the ecliptic. Now, I say probably and believe because we've actually never seen a comet in the Oort cloud. These comets would be way, way, way too far away to verify that the Oort cloud exists. So while the Kuiper belt has been truly discovered and well observed, the Oort cloud is a very well motivated, but still largely theoretical region of the solar system. There is one observation that might point the way, and this is an object called Sedna. Here is one of the discovery images of Sedna, and again, it's just a tiny speck of light. It is so small that even Hubble couldn't really resolve it. Here are two images of Sedna from Hubble. On the right is the stationary image, and it's the best image we could get of Sedna, and it's so few pixels that you really couldn't figure out the size of Sedna from it. What we had to do is shown in the image on the left. We let Sedna drift across the field of view, and we measured the thickness of the line it left on the image, and using statistics, we could then measure the thickness of the line and estimate the size of Sedna. Sedna turns out to be like a large object found in the Kuiper belt. It's about 3/4 the size of Pluto. But what makes Sedna special is it is located beyond the range of the Kuiper belt. Its orbit stretches from a perihelion of 76 AU all the way out to an aphelion at 840 AU. This is a no man's land in the solar system. It's outside of where we expect to find Kuiper belt objects, but yet it's inside of where we expect to find objects in the inner Oort cloud. And if you talk to the theorists, they don't really know why it exists there. Remember that when we were talking about the scattered Kuiper belt objects, all of their perihelions scattered off of Neptune. They were in close to the orbit of Neptune, so that you could see that the scattering of Neptune pushed them out to these large radiuses. What is at the distances of like 76 AU or 840 AU that would scatter Sedna to create this orbit? Or maybe Sedna is like Pluto when it was discovered in 1930. Maybe it is just the first object in a yet-to-be-discovered population. Here's a movie that shows Sedna's orbit and sort of recapitulates what we've covered in a lot of this lecture. Starts out showing the inner solar system orbits, the rocky planets, and then the asteroid belt around that, quickly moves through the giant planets, Pluto's orbit, and the Kuiper belt. Here is Sedna appearing outside that, and you can see Sedna's orbit well outside the Kuiper belt, but it's also well inside the confines where we expect the inner Oort cloud to be. So, finally, in this lecture, I want you to recognize that we have reached the edge of the solar system. This is an artist's depiction of what it looks like at the radius of Sedna. Note the sun over on the right-hand side. Recognize that the human eye has a resolution of about 1 arc minute. The sun, as seen from Earth, is 30 arc minutes. As you move further from Earth, the sun gets smaller on the sky, roughly linearly. So the sun from Neptune would be 1 arc minute, and to the human eye, it would be unresolved. From any object out in the Kuiper belt, the sun would look just like any other star in the sky. Now, it would be overwhelmingly the brightest star, but still just another star. And if you go all the way out to the 50,000 AU of the Oort cloud, the sun wouldn't even necessarily be the brightest star at all times. Other stars in our galaxy could move close enough that they would be brighter in your sky than our own sun. This is out so far, it is where our solar system merges with the Milky Way galaxy. Next time, we will discuss the reorganization of the solar system that is inspired by these discoveries of the Kuiper belt and the Oort cloud. This is the 21st century view of the solar system, and we'll discuss how it changes our view of Pluto and forces us to reconsider just what a planet is. We'll see you then. Take care.